All right. Well, welcome everyone. It's 6 o'clock, so it's time to get started. Welcome to Universal Family Night for the Arizona Science Teachers Association Science Teacher Symposium number 8. Tonight we have Dr. Kevin Hainline talking about the James Webb Space Telescope. Dr. Kevin Hainline is an astronomy professor and researcher on the James Webb Space Telescope, JWST, NIRCam science team at the University of Arizona's Steward Observatory. His research focuses on hunting for ultra distant galaxies from the dawn of time, supermassive black holes that grow secluded by dust, and cold brown dwarfs at the edge of the Milky Way, using the unprecedented power of the James Webb Space Telescope. He received his PhD from UCLA in 2012 and spent 3 years as a researcher and professor at Dartmouth College in New Hampshire before moving to Tucson, thank you so much, to work on the James Webb Space Telescope. Kevin has a passion for science, outreach, education, and has spoken about astronomy and our relation to the stars at events around the world. We are so excited to have you, Dr. Hainline. Thank you so much, and take it over.
Great. So let me share this keynote this is what I wrote here for you all. I hope you're all having a wonderful evening. Some of you have seen me speak before. Some of you never seen me speak at all. I love talking to Arizona science teachers, both in person. Last year I was at Flandreau, and over Zoom I've done this a couple times. It is a real honor to get a chance to talk to science teachers. And tonight I'm going to, tell you about something really exciting. So as was just said, my name is Kevin Hainline. I'm an associate professor here at the University of Arizona. Bear down, go Wildcats, whatever. And tonight I want to talk to you about what we're made of. And that was kind of, I think, Danelle told me, the theme of this whole thing is, about how we're all made of matter. And I want to talk to you about the origin of matter. And when I talk about matter in kind of our astronomy sense, mostly what you interact with is something called baryonic matter, or the word baryon just means the stuff you touch and interact with. But there's a whole other part of the universe that I'm not going to talk about. You'll have to invite me back in the future, although I don't really research on that. But dark matter, dark energy, these things that are more kind of like physics ideas that are very important for astronomy as well. But tonight we're talking about baryonic matter, what we're made of. And so as was just said, I work on a space telescope that I wonder if the first time I spoke here, it was before it launched, and I was talking about how excited I was. And now I'm talking a lot about, how exciting it is as opposed to it will be. I'm going to be talking about this telescope that I work on, which is called JWST. This is a picture of JWST, like an artist's rendition, because in actuality, if you were floating out in space and saw it, it should not be this bright. Otherwise, something has completely failed. JWST always sits 1,000,000 miles away from the Earth, secluded in darkness, because we don't want any light hitting the telescope except the light we care about from distant objects. And it is a massive, massive telescope, the size of a tennis court, with this beautiful giant 21, 22 feet across mirror that is gold-plated little hexagon segments. It was launched, in December of 2021, and it's been going for years. And like now, it's a very exciting thing because it was designed for like a 5-year mission, but it's probably going to live that for a lot longer because it was really launched very well. And the thing is I've spoken about the launch and the excitement of that for many years. I want to talk to you about what we've discovered using the telescope and what we understand about the universe from observations with the telescope. And I kind of want to tell you about the history of the universe and really the history of matter. And so let's talk about matter. Here's a diagram you've probably seen, but colored in a way maybe you haven't seen. And so let's actually click on this. This is an amazing figure that I love because it is the periodic table, something that growing up in almost every one of my science classes, I could look somewhere in the room and see the periodic table. And for many of the students who are in your classes, they probably are bored by this. And I'm sorry, it's just inherently, it seems like it's a pretty boring thing with a bunch of letters and numbers. But when you unlock it and understand what it is and understand its history and what it really tells us, it seems like a cheat code to the universe. Because it's essentially, here's everything we've ever discovered that makes up everything around you. And the version that you have in your classrooms probably, says a little bit more information about atomic weights and other things. But this version I like because it's colored based on astronomy. It's colored based on what had to happen in the universe such that that element could exist at all, which is pretty special because we talk often about things being star stuff or we're made of stardust, but it's more complicated than that. It's not just star dust. It's stuff that had to happen with stars and around stars. And tonight, I want to talk to you about the history of the universe and what we've learned from JWST and other astronomy ideas that led to this diagram. So let's just first start off by looking at this diagram. Up in the top left and top right are, elements 1 and 2, hydrogen and helium. They are the most abundant elements in the universe of the baryonic matter, and they were made in the Big Bang, which we'll talk about in just a second. But then below that, you have a lot of other things: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and these have a variety of other origins. So you can see that a little bit of the lithium in the universe also came from the Big Bang, but that's it. There's no blue anywhere else. That dark blue only exists in hydrogen, helium, and lithium, meaning the universe only at the very beginning made those elements. And then you start getting things where you're seeing like merging neutron stars, exploding massive stars, dying low mass stars, exploding white dwarfs. That literally means that every time you interact with something, this incredibly crazy idea, something like 2 neutron stars merging had to happen, or a star had to explode for you to be here. This is one of the great secrets of astronomy, is when you learn about how the elements were formed, you're actually learning about how we were formed, right? We're made of carbon, we're made of hydrogen, we're made of nitrogen, oxygen is what we're breathing. And all of those elements came from stars that lived their lives and then died, sometimes as low mass stars, sometimes as exploding high mass stars. It's very, very exciting to think about how if you trace the element origin of every one of the elements in our fingers and skin, if you just trace them back in time, they were inside of stars, and not just inside the edges of stars, put together in the cores of stars. But I'm getting ahead of myself. We're going to get to that point at some point in a little bit. Let's start with just hydrogen and helium, and let's start with the Big Bang. So in the beginning, it was dark, and the universe was born in the Big Bang. The Big Bang is not a thing that happened at one point in the universe. It happened across the universe everywhere, and it was an incredible energetic explosion of light. The entire energy of the universe was born in one massive explosion of light. And so at one tiny fraction of a second, all energy was light. And the universe expanded and cooled, and that light, miraculously, and this is a process that's very complicated, it started to become particles. Hydrogen came out of just the light, just protons. And there were electrons floating around, and for a long period of time, that's what the universe was. Hydrogen and the energy was enough to make a little bit of helium. Every once in a while, those two hydrogens would crash into each other. And for a long period of time, that was the universe. The universe was literally this enormous ball of hydrogen cooling off. Hydrogen, a little bit of helium. There were no stars, there was nothing. It was just cooling hydrogen. It was so hot that those electrons didn't want to hang out with the protons, didn't want to hang out around the atoms. They just were free to wander all over the place because it was just so energetic. There was no neutral hydrogen, we call it. But at a certain point, the universe cooled off and expanded, and eventually those electrons kind of started hanging out with the hydrogen, and becoming neutral. And then we had a universe that was just full of neutral hydrogen, just slowly pooling together by gravity. And that was it. If you had a periodic table back then, it would literally just have 3 little boxes: hydrogen, helium, and then at the time, lithium. Astronomers like to have a periodic table that's just 3 boxes, where they lump everything that's not hydrogen and helium into one big box they call metals. I'm not kidding. When we talk as astronomers about the metallicity of the universe, we're talking about anything heavier than helium. So if you are a chemist, you should probably wince because our periodic table is so much easier than yours. It's just everything else is metals. And eventually, the hydrogen and helium was pooling together by gravity and becoming these large pools of hydrogen and helium that gravity was pulling down. And as gravity pulled it down, the particles moved faster and faster until at the very centers of these dense pockets of this simple gas in the early universe, you had stars being born. You had this process where the pressure was so high on these little hydrogens. And hydrogen, when you put them together, they don't want to come together. They don't like each other very much because of electromagnetic repulsion. But if you get them close enough together and you have them moving fast enough, eventually they'll get so close they realize they actually have more in common than they have that separates them, and then they become a helium. This is a process called fusion. It takes the pressure and energy of an enormous gas cloud of hydrogen to pull down to make this happen, but it releases a tiny bit of light. And that light goes out and strikes other hydrogen in the universe and causes the electrons to get knocked off, such that what you start having are these little baby stars that are starting to essentially hit all the electrons and make these big pockets in the universe. So here is this artist's rendition of how the universe starts getting cleared in these pockets. You're going from this long period of time, like hundreds of millions of years of the universe dark ages, to a period of time where the universe starts to have its first stars in its first galaxies. And we're going to come back to that at the end of the talk. But for right now, this represents the second major phase transition of the universe. Because those stars, as they start putting elements together in their cores, don't just stop at helium. They start putting other elements together. They take helium and put it together to make carbon. They make oxygen. They make these other elements in their very cores. And so if we were to put this whole thing on a diagram and put the Big Bang up in the top left and time going down to the right, you can see the dark ages up in the top left, and then it says clearing begins as you start getting the first stars and the first galaxies. And then inside of those galaxies, you have these stars that are starting to put the elements together on the periodic table. But as you know, right now, we're not in the centers of stars anymore. You are not sitting in the center of a star. So something had to happen to that star such that you could be here as a bunch of carbon that was put together atom by atom in its center at some point. So let's look at some actual data. I've just shown you some fun artist renditions. I'm very proud of that Big Bang graphic because I was entirely in Keynote. I was really excited to make it. But let's take a look at what JWST tells us about how stars are born and live their lives in these gas clouds, because that helps us understand the processes that went into making atoms. And if you're really bored by what I'm talking about, at least this gives you a kind of thing you can zone out to. You can like mute me and put on some really calming music and just look at some of the pretty pictures I'm about to put on. So here is a picture of the Serpens Nebula. And this is a picture taken with the camera on, I work on the team that made this camera, NearCam, because they're taking a picture in the near infrared, which allows us to see through a lot of the dust that might otherwise block our view of this beautiful star-forming region. This is located 1,300 light years away, 1,300 light years away. So the light we're seeing left those stars, these baby stars, 1,300 years ago. I don't know what you were doing 1,300 years ago, but I know what the stars here were doing because we have a picture of it. And it's a thing where we're seeing a big gas cloud called a nebula. Nebula is just a fancy word for fuzzy, because when you look at this through a telescope back in like the 1800s, it didn't look like a star, it looked like a fuzzy thing. And they said, well, we can't call it a fuzzy. We have to call it something fancier than a fuzzy. What about nebula? That's what they called it. And this is the nebula, which is a big gas cloud where baby stars are being formed. And you're actually seeing a lot of the baby stars in and around this nebula because they're causing a lot of these jets. There are these like finger-like protuberances, and you can see most of them up in the top left corner of the image. I don't know if I can do this, maybe you can't see that. Those are some of the jets from the baby stars being formed, because baby stars aren't like baby humans, or maybe they are, and I should just watch out for my metaphors, but when baby stars are formed, they make these eruptions out of both ends. Actually, they may be a lot like baby humans. I'm going to show some closer up images of them, but I don't want to take the metaphor too much if you have family around. But the baby stars make these big jets that plow their way out into the universe. And these baby stars, gas is falling onto them to help heat them up and make them very hot in their center as they start the process of fusion, putting atoms together, atom by atom. You can see in the very center, there's this thing that Hubble, when it saw it, was called the bat shadow. And it's, now we can see with JWST, that's a lot more complicated right there. And there's like all of these really incredible layers of gas and dust. And astronomers study this because we can study the chemistry of this gas and dust to understand what are the stars being made out of in these. The chemistry is encoded in the colors that we see. We take pictures in very specific filters because they can highlight things like hydrogen or carbon or oxygen emission I study oxygen all the time. And in fact, my grad student and we study oxygen from the dawn of time, which is very exciting. I'll come back to that later on. But I think it's pretty wonderful to look at all this and see, once you get around a lot of the dust, you really can see some beauty. To highlight that also, here is a picture of a different nebula. This one is in another galaxy. It's 200,000 light years away, this image. And so you could imagine the last image, we're kind of zoomed in on something because it's a lot closer. We can see it with better detail. We're like zooming out to look at an enormous group of stars. And you can see on the left that all of these stars, have some brown dust and stuff. But on the right, you can see with JWST that we can see through a lot of the dust to really understand the beautiful hydrogen filaments of gas that are fueling baby stars. And so this gas, hydrogen gas, this is what happened early on in the universe. There's a lot of hydrogen. The hydrogen here is like 10,000 degrees Celsius or 18,000 degrees Fahrenheit. And the orangish gas is dense hydrogen, which is a lot colder, maybe negative 300 degrees Fahrenheit. And so you're seeing in this one region really hot gas and very cold gas because stars are heating it up. And then the denser gas, the orange you're going to see is kind of in denser pockets. That dense gas is cooling off and forming new stars. This is chemistry. This is how the atoms from the early universe go to make baby stars. And like you need cold gas to make stars form. If the gas is too hot, it doesn't want to settle down. And you know this because you've presumably had to deal with rambunctious kids. How do you get them to settle down? Well, if they're all moving around, nope, not going to settle down. But when they're seated, that's like cold gas. Then they can start to learn, right? And so the same thing, you really need to make gas very cold. You need it to slowly cool off before it can coalesce to make new stars. It's fun to see Hubble versus JWST because the universe looks a lot different in the near infrared. Here is a zoom in on one of the jets from a star. Now I'm going to have to explain this because we're not actually looking at the star and we're seeing how things I care about, like galaxies, kind of can trick you. So there is a star off the bottom left of this image. I'm not showing it. I'm showing the jet because the people who took these images, they don't care about the star as much as they care about the chemistry of these jets. They care about what happens with gas that flows off of a star as it's being born. But the thing is that well behind all of this, there's dozens and dozens of galaxies. You can see them all. They're all the little smudges, including this beautiful red and blue one that looks like the jet's coming from it. But no, it just is a chance occurrence. It's just photobombing this image, standing in the background, giving the peace sign, saying, I'm a very beautiful galaxy. I happen to be a lot farther away than the other ones. But what you're seeing here in this reddish orange color is the outflow. And it gives these clues about how a baby stars form and how that jet activity influences the environment around it, because the jets help turn off star formation. And they move many, many, many light years away from these baby stars. They're really, really big. You can see it kind of looks like, imagine a boat was driving up to the right and you get this like a wake behind the boat. That's what's happening. The material is just plowing through the interstellar medium, the gas between stars, and causing this crazy thing. It's beautiful. It's like a wake around a boat. And we're getting more molecular hydrogen, and also carbon monoxide is what we can see here. Carbon monoxide, something you probably have a carbon monoxide detector in your house. If you stuck that carbon monoxide detector here, it probably would not be able to detect it because what you're seeing here looks like it's dense gas, like you'd fly through this and cough, oh, too much, oh, but no. This is such a big region that it's incredibly, incredibly tenuous gas. It's dense to astronomers because we can see it, but in actuality, the particles are not very far close together. That's the thing about the universe, is that even when it looks like it, oh wow, this would look beautiful if I was floating in front of it, but we need incredibly sensitive telescopes like JWST to see pictures like this. Here is another baby star, a protostar, which has these bicone, like these two outflows either way. Like I said, this is LINS 483. It's 650 light years away. And you're seeing here that you get these like asymmetrical lines and stuff as light peeks out and pokes out on either side. And you still have a bunch of dust, And why that matters is that when we look at this, our sun had to go through this process 5 billion years ago, 4.5 billion years ago. And the dust and gas that flowed in eventually spiraled around and made baby planets like the Earth. So the Earth was made at the same time as the sun was made. They were made together. And so by studying something like this, we can see that process going on in other stars in unprecedented detail, where we can see through a lot of the dust to understand how are baby planets made and disks around baby stars, and what goes on around them when you look at these jets. And we think, did the sun have jets? Well, probably. It depends on how bright it was early on in its life. It's pretty beautiful. If we zoom out farther, we just looked at a couple beautiful, beautiful stars. If we zoom out a little farther, we can see this is maybe my favorite picture. I'm trying to also highlight pictures that have been taken in the last year, because if you're someone out here who's been watching me give talks, you're like, okay, I've seen this. Some of these you haven't seen. This is one of my favorite pictures that JWST has taken in the last year. And I urge you, on your own time, or maybe on your phone right now, find this picture in high resolution. It's like my background on my phone. I absolutely love this picture. It looks like an ice cream dream. This is NGC 602. It's another cluster of stars that are formed in a different galaxy, another galaxy just right next to our own. And so what you're seeing here is you're seeing a baby group of stars. They're not all protostars like we were just looking at. They're kind of like a classroom of stars. Like you, Arizona teachers, teach essentially groups of stars that are this old. I mean, they're like in terms of the lifetime of a galaxy or of a star, this is very, very young. And what you're seeing here is that these stars have had an impact on the region around them. Because the stars are glowing and lighting up, they've created this big cavern, this big pocket. That's what you're seeing, a big pocket, like a bubble that's been inflated by all of the stars as they give off their light. That's why all those fingers are pointed in towards the center of the bubble, because those fingers represent denser pockets where, as the bubble's been inflated, they haven't been able to push that away, right? Like maybe you've been out with a hose trying to get rid of stuff on the sidewalk, and maybe there's a dirt clump and you hose it down, and the water's spraying, but that dirt clump's really, really dense. That's what you're seeing. You're seeing denser dirt clumps, dust clumps, gas clumps, that the light is not doing as good a job clearing this out. Our sun used to be in a cluster like this, but then over time, our sun and the sun's brothers and sisters, siblings, pushed all the gas away, and they were just left with a big a big star cluster. And that big star cluster, eventually those stars kind of, just like your students won't stay in your classroom forever, they eventually by gravity were put out into the rest of the universe, rest of the Milky Way, to essentially live their lives in isolation. And so you can see, here's another absolutely beautiful one of these types of this is another group of stars that's an extreme outer galaxy. It's 58,000 light years from the Milky Way, but it's a tiny, tiny little galaxy. And you're seeing here, because with NIRCam and MIRI, you're looking at all of these little groups of stars, and many of these stars are in the process of slowly moving away from each other and moving out, right? There is some newly formed stars in the very center there, little baby stars, and you can tell because you can see the jets. Can you see the jets? Like little asterisks poking out, like little lines poking out. Those are some baby stars. But many of the stars that you see there in this image are stars within our Milky Way that are just living their lives. They're just taking simple elements, hydrogen and helium, and putting them together in the very center. Those stars, as they live out their lives, eventually some of them will become large enough that they will have in their cores taken that leftover helium and made carbon or made other elements. And in some cases, those stars will have what I like to think of as burps, where they just start puffing out outer layers, like carbon and stuff, into the universe. And those will collect to make new gas clouds, to make new stars. For many stars, if you want to unlock how do you get the stuff that's in the center, all of these heavier elements, how do you get them out? Well, the star needs to die. So this next image is a JWST image of the Ring Nebula, which is the leftover remnant of a star kind of like our sun that died a long time ago. And so it's only 2,500 light years away. You can actually, with a small telescope from the Earth, you can see it as a little tiny ring, but with JWST, you see it incredibly beautifully. And when our sun dies in like 15 billion, not a long time, 5 to 10 billion years, its outer layers will puff off into the universe, leaving behind a little white dwarf star in the very center, which is its core, mostly made out of carbon. But in that outer envelope will be a bunch of other carbon and other elements that will puff off into space. If you remember, I go back to here, this is dying low mass stars. So lithium, carbon, nitrogen, some of these strontium, yttrium, barium, hafnium, like these are elements that came from a star like our sun dying in those outer envelope layers, which is pretty cool. The white dwarf that's at the very center of this, the remnant core, maybe those white dwarfs at some point, they might also, if I come back to here, like they might also explode. In the process of exploding, that's very energetic, and you get things like silicon, which powers the phone I'm looking at right now to talk to you. Silicon what had to happen to make silicon is that two stars or a star had to live its entire life and die, and then in its explosions, these like crazy explosions that happen when enough stuff falls onto them, you get that element and it puffs off into space just like this. This gas will float through space for millions, billions of years and make new stars from it. And in those new stars, you get the elements that will coalesce to make the new planets. And then we dig that out of the ground, which is really crazy. For larger stars, you get explosions like this. This is the Crab Nebula, which is a remnant of an explosion that happened in 1054. We have evidence from other cultures, Chinese, Native American, like in Arizona, there's evidence that they saw this star exploding in 1054 AD. And now we look where it is, where they charted where this explosion was, and we see the remnant of the explosion. This is not like the kind of like beautiful puffing out of the star's outer layer. This is a thing where the core collapses and the rest of the star explodes, and it really shakes up the environment around it. This is a very, very energetic process, and a lot of that energy needs to go somewhere. And so that energy goes into making heavy elements. If I come back here, exploding massive stars, boom, you're breathing some of it right now. In your breath, filling your lungs, is gas and elements that came from a star that had to explode. Sodium, you just put it on your food. You're like, oh, I'm just going to put a little exploded star on my food for flavor, right? Think of it. Aluminum. I'm going to wrap my baked potato in what came from an exploding star to stick it in the oven, right? It's really, really absurd to think about how we just dig it out of the earth and stick it in foil in our drawer. And it has a cosmic origin. A star lived its entire life and exploded. And in the energy of the explosion, aluminum was born. That's it. Pretty cool. Even crazier, and I don't have any highlighting this because it's more like a thing we know will probably happen, but you can see this merging neutron stars, this orange for things like gold and silver, 47, 79. Merging neutron stars means you have to have two stars that live their entire lives and then died, like here. In the very center of this is the core of this star after it exploded, and it's spinning very fast. It's called the Crab pulsar, and it's a neutron star. And if you had two of these, two stars that lived their entire lives in a binary orbit, and then one of them died, and then later the other one died, leaving behind these beautiful, crazy explosion nebulae, over time, they'll spiral in, and in that crashing instant of those two stars crashing, that's how you get gold and silver, like my wedding ring. This wedding ring, I just wear it all the time as a symbol of love, but also as a symbol of two stars that had to live their entire lives and die, and then their cores had to coalesce over millions of years so that we could have it and dig it up out of the earth. Meanwhile, by the way, diamonds is just carbon being squished together. Not as exciting. Silver and gold, that's where it's at. So every time that I make a joke, I assume everyone is laughing at home. I don't hear it. I'm sitting and doing a Zoom talk, so I have no idea, but I'm just assuming I'm really killing. This is very funny. So let me take a step back and talk about the fact that we have all of this incredible evidence in our nearby universe from JWST, in the Milky Way and around from JWST. But the real question is, is this going on just in the Milky Way or other places? What happens beyond that? Like with those things in the background of this image here? Well, it turns out, and this is what I study, there are galaxies like the Milky Way and very different from the Milky Way in every single direction. This is a small, tiny chunk of the sky, like a grain of sand held at the end of your arm. That part of that amount of sky, that's what I'm showing you right here. This is part of the JADE survey, which is the JWST Advanced Deep Extragalactic Survey. If I were there with you right now, I think I have them right here. I could pull out and hand out some JADE stickers that I have. I am one of the key members of JADES, and I am like such an expert of this field that I was in an office at Harvard last week, and someone had a picture on the wall, and they're like, I don't know what part of the JADE survey this was, and it took me about 5 minutes to figure out where it was because I've looked at this a lot. And the thing is this is only a tiny chunk of it. Let me actually show you. This is this, which is the public data release of JADES that's out right now. And to give you context, if you've ever, while growing up, seen this very famous Hubble Ultra Deep Field, the deepest data Hubble ever took. The Hubble Ultra Deep Field is literally just this one tiny chunk of JADES. And the thing is, we're about to put out another data release that's a little bit bigger. And I'm going to show you what our current data release is just for this part of JADES. But I have to zoom out because I can't show it all in this one. So I'm going to zoom out right here. And this is our data release for JADES. It's over twice as much as what I just showed you. And that's a tall order. And you can see that it stretches and encompasses many different surveys. And I am a person whose job is to look through all of these galaxies and figure out which ones are the farthest. So I'm writing a paper right now with some of our bigger candidates, which is very exciting. So coming soon, you'll be able to look through every one of these galaxies in what we have is a FITSMAP software. Right now, you can look through our public data release through the FITSMAP software, and I can show that at the end of this talk. But one of the exciting things about JADES was that in the first couple of years of exploring JADES, we were very fortunate to find what at the time were some of the farthest galaxies humans had ever discovered. And so right here is a plot. This is a kind of a complicated plot of galaxy brightness on the y-axis and then essentially the wavelength of light on the x-axis. And these three galaxies were for a time, for many years, this GSC 14.0 and 13.0, they were the farthest galaxies humans have ever found. I talked about this last year because last year the Guinness Book of World Records had just been printed and it said that 13.0 was the farthest galaxy, but it was printed, and before it was printed, a new record was broken by our team to find 14.0, and that was farthest. And then in that paper, we found one that was also farther than 13.0. But for a time, these were some of the farthest galaxies humans had ever seen. And it was really exciting because they were very bright and very interesting and very different. They had lots of stuff about them that were really, really amazing. And JSC 14.0 was especially bright, and we really had a hard time wondering, is this alone? Are we going to find anything else that is any way approaching this? And if you want, Space Telescope made this beautiful video just to really show you how far back, right? So here is JADES in good south. I just showed you this. And if I go forward, and hopefully this looks all right on your computer, we can start zooming back in time. Every dot you see is a real galaxy. And these are at the distances that I've predicted them to be at, which we do pretty well. You can slowly fly faster and faster, farther and farther backwards into time until you get almost all the way back to the beginning of time. Because this galaxy, the light that we're seeing, is from so far back in time that the universe was only 290 million years old. JADES GSC 14. That's like a really, really amazing idea. This idea that we're seeing a galaxy from when the universe was a baby. My graduate student, Jake Helton, who's defending his thesis in 2 weeks from today, good luck, Jake. Jake and I looked at this object using another instrument on board JWST and discovered that in this galaxy, only 290 million years after the Big Bang, 290 million years, which is like, if the universe were a 2-hour movie, this is a little less than 2 minutes into the 2-hour movie. If the universe were Star Wars, we've gotten through the crawl, we're just meeting C-3PO. That's when this universe is. C-3PO, one of the main characters of Star Wars. Everything that happened after that happened later than after we see this galaxy. And in this galaxy, we see oxygen gas. Oxygen gas, I showed you earlier, needs a universe where stars had to live their entire lives and die. A star had to live his entire life and die. A bunch of them did. so that we could see oxygen gas lit up in the way we see it here. That means that stars came on the scene pretty early on. And this is a pretty big galaxy compared to what we predict. And for a while, this was it. We thought this was like a really bright, really crazy object. We're like, we hope we find other ones. And then 2 weeks ago, another team, independent team, looking through data, got a spectroscopic confirmation of this galaxy here. This is MOM Z14. MOM stands for mirage or miracle. And in this case, it was a miracle. This galaxy breaks the record that our team set slightly farther. It's really, really bright. It's not as bright as GSC14, but it's approaching it. And it has evidence for carbon, a little potentially oxygen gas, and the person who did a lot of the fits for this was my former graduate student and former University of Arizona graduate student, Raphael Wieding. And it's a very, very exciting thing. This is a galaxy that is at 14.44, breaking our record by just a little bit. We're only looking back a little bit tinier backwards in time. But it's amazing that we're able to see this galaxy and see that the galaxy has complicated physics and complicated elements, meaning that periodic table that I showed you right on the top was starting to be put together much earlier than we ever thought possible. When JWST was launched, the farthest galaxy was at a redshift of 10.6. 10.6. And we thought, oh man, I don't know what we're going to find, but probably it'll be very, very, the periodic table will be very simple. But it turns out the periodic table is not just hydrogen and helium. There's already a nitrogen, carbon, oxygen. We're seeing all kinds of stuff in many galaxies from this early era, what we call cosmic dawn, the frontier of our ability to understand back in time. And so now you might be wondering, so what, Kevin? Why do we care about this? Well, maybe you're excited by this because you like astronomy, but you look at a periodic table, some of you are chemistry professors, you understand the chemistry of atoms and these things, and that's important. And maybe this is what your students might be saying, so what? Well, it turns out they came from somewhere, and we have pictures of it, which is really exciting. But I'm about to switch over, and if you're there with your family, I'm sorry if it's about to get boring, but this is a pretty important thing where I hope that I'm not going to try and get political, but I want to talk about something that is weighing on my mind and maybe weighing on your mind, which is this idea that in the last year, all of this incredible science has been kind of facing a backlash. We're seeing lots of things where we're getting cuts to science funding. This graph on the bottom right, where you just see how all of this funding is just slowly being eaten away, I argue that's pretty bad. Because the thing that we just saw, what I just showed you, these pictures, that literally are just from the last year or two, they are telling us where we came from, giving us an understanding of who we are at our very core, how we were put together. And that only happens because we, as a human society, invest in science and care about science and want to do science and study the universe and the natural world. And people are losing their jobs. And some people are going to Europe, but there's not a lot of jobs in Europe because they've got a bunch of really great European scientists. And I'm saying this because maybe I get a call next year from Danelle being like, hey, do you want to do this? And I say, well, I'm not a scientist anymore. I don't have a job. That is a real possibility because the funding that I depend on is also going to go away. And that's bad. I would argue, maybe you're like, it's okay, we make do. But hopefully you also, because it turns out that this all comes from an idea, which is that we also are in a time when people don't trust science. They don't trust science. We have, we don't trust science morals, apparently. We don't trust scientists. We think that maybe science is something where we have an agenda. I will tell you, I do not make a lot of money. You can look up almost every scientist's salary online and see, and you generally find out that most scientists aren't doing it for the money. I think a couple are, and those are jerks. Most of us, we're doing it because I have a curiosity and passion in my very core, all the way down to the center of me that says, it is exciting that we are seeing things that no one has ever seen before and understanding the universe in a way we've never seen it before. And so this is frustrating. And people ask me, well, how do we get science back into the public eye? How do we get people to trust science? And it's exciting. I'm talking to science teachers because I think you play an incredible role on the front line of doing this. You are vital. There's a lot of talk in science and in higher education about this leaky STEM pipeline. This idea that like, oh, we've got all these ninth graders, and then only some of them graduate high school, and some of them go to college, and look at how many at the very end become STEM graduates. But I would argue, especially for primary, secondary school teachers, that all of this stuff down here, this leak, those are not, we don't abandon them. Those are the public. And the public then, at some point, they stopped learning about science, maybe after ninth grade, maybe after high school, right? They leaked out into the public and became citizens. And then that means your job as people who are part of the earlier parts of the pipeline is fundamentally important because you dictate the thoughts and ideas about science and about not just the facts of science, but the fundamental belief in science and what science is. It's not a thing where we're trying to get truth, but actually it's a process where we're wrong all the time and we make mistakes and we do it because we're just naturally curious. Curiosity is fundamental. Science is a weird tool we've developed to help understand human curiosity and develop curiosity. And so I'm going to show this again, the origin of the solar system elements, but I'm going to color these a little bit differently. I'm going to color these. I'm going to name this instead the origin of my scientific knowledge. Where did I get the knowledge I take around as a scientist? And it turns out it wasn't just me doing research. In fact, it started with primary school, setting hydrogen and helium, which, the bulk of everything that I know and the way that I interact with the world, the numbers. Like, I remember my math teachers doing times table exercises, and I thank goodness because I have to do that type of simple math all the time, right? I remember the first time seeing a periodic table. I remember the first time learning these sorts of ideas about how the universe works and the solar system. The books that I read as a child, the science books, also impacted that. But then my secondary school education essentially just opened up everything. If I had a curiosity that my primary school education helped form, it was secondary school. It was the teachers that I have that I can name: Mr. McFan, Miss DeBow, Miss Lingle, like these teachers that I can name in my elementary through and mostly in high school, who essentially took me and said, you know what, you have a curiosity. Let me show you some cool tools. Let me show you physics. Let me show you chemistry. You're going to dissect an earthworm and it's going to feel real weird, but like at the very end of this, you're going to understand about how things are put together and the insides of creatures through evolution, right? And then we go on. Yes, a big chunk of what I learned came from my college education and also from my graduate school education as well. And then there's things throughout that also my research experience is filled with. But look at this. This is a diagram that shows, and I truly believe this, that a huge foundation came from the work of science teachers. And so my end thing right now is that we are in a period where it's actually fairly scary for science in this country. And what that means is, and maybe you wish that other people besides scientists, maybe people who paid your paychecks or whatever, thought about this, but I believe that your job matters more than ever. If we are going to combat an ascientific, like a walking into the darkness where we're like, misinformation is everywhere, and think about critical thinking skills, think about science ideas, and think about science not as like here's one way of thinking about it, but rather here's a way where we should think about it because it is the best way we've ever learned to think about things. As opposed to just like, well, I read it, or, oh, ChatGPT told me, so I guess it's true. But rather, oh, you know what? A bunch of pretty smart folks thought about it, were wrong about it for a little while, and then got new ideas about it. That seems to me to be a lot better way of looking at things that I want to trust in than, well, one person who's put in power says it's the case because they had a hunch or they heard someone tell them this is what would happen with them. So your job as science teacher matters more than ever. I'm going to keep this up there. I think that I'm just about at the end of my time, and so I'd like to answer questions for about 10 minutes. And if you want to, type it into the chat, or I think we have a moderator, I'd love to answer questions about all kinds of stuff, space and JWST, any question you might have. Thank you very much.
All right. Thank you so much, Dr. Hainline. I know every time I hear you speak, it just boggles my mind. And can't even figure out. But we do have a few questions that come up. First one is, so on your elements, TC and M or PM, they're not found in the universe? Those are colored gray.
It's that they're found, but we don't exactly know how the universe made them. Now, this diagram is really helpful, but also this diagram is still up for debate. People make new versions of this where like, actually, oh, it can't be this. Like, some of these technetium, I think TC, man, I apologize. I don't know my really, really rare earth, like, and there's a bunch down here that are man-made as well. But like, we think that it probably is something made, but we don't actually know. This is not like an official science. Like, this is not something where like, the astronomers all got together and said, let's make this. This is something where groups of scientists who work on astrochemistry got together and said, like, I think this is our best guess. And so, there's things, right, that we're like, I assume every time I say something that's wrong and a bunch of chats, just like the chat notifications, I apologize. I should learn my periodic table abbreviations. Everything's in metals. Remember, I'm an astronomer. It's all metals.
Great. I like that. Another question was, so were the stars that formed closer to the Big Bang larger than ones forming now, or was the energy just distributed differently?
We think that because of the fact that the earliest stars were fairly pristine, many of them probably were much, much larger. Maybe the largest star that we have, that we know of, is maybe 100 times-ish the mass of our sun, like 100 suns worth of stuff. And these probably were that and larger. The problem is we've never seen any of those. We call these population 3 stars for stupid historical reasons. And these population 3 stars probably were a lot larger. And it turns out you need some of these heavier elements to help the gas fragment as it collapses into smaller chunks to make smaller stars. But when it's very pristine meaning just hydrogen and helium, that's what we call pristine. Astronomers really aren't fans of other elements because they're more complicated. Hydrogen and helium, so simple. But when it's more pristine, that gas allows for larger stars. But yes, good question.
All right. Another one was, I recall seeing somewhere that pictures from JWST arrived in black and white, and then the scientists apply the colors. How does that happen?
Yeah, so let's look at a pretty color picture here. So the thing is black and white and color, every image that's ever taken with your camera is black and white. You just don't think about it that way because they serve it to you in color. When pictures came out, like the way that photographic plates work is slightly different than the way that all digital modern cameras work. Your camera on your phone, the one I'm looking at right now, the webcam you're looking at, has sensors that are sensitive to red light, green light, and blue light. And they take individual pictures where when they come out, they're black and white insofar as that you could color it white where it sees light, black where it doesn't see light, right? Imagine that you had a big group of buckets in a rainstorm. Maybe the rainstorm, maybe it's like across, like the entire city. And at the end of the day, you said, okay, how much water fell in the rainstorm buckets across the city? And you could see like, oh, there's a bunch over in this part of the city and not a lot over here. And that you could color that by like, okay, well, if it's the bucket's full, I'll make it white. And if the bucket's empty, I'll make it black. Then you'd have a picture that showed you could put it over the city map that shows you where the water hit. And that would be a black and white image. And similarly, with JWST and with all modern space telescopes and telescopes, we take pictures through filters that block out all light except the light we care about, and then we color those black and white, those images black and white. Like I'm always looking at black and white images because it's easy for me to go, oh, I know the white is where I have signal in that filter. To make the color images, we take a series of those images and we say, okay, this black and white image, I'm going to assign a red color, and this one a green color and a blue color, or maybe multiple different colors to add up a lot of filters together, therefore creating your final color image, where instead of it being black and white, you're saying black and then red, black and blue, black and green, and then you add it all together and they make these beautiful color images. And they help astronomers essentially study, like I was saying here, the different colors, in this case, are from different filters that focus on different parts of hydrogen. And so the images, and I could give a whole talk on this, on how we do that, the images teach us about the chemistry. So it's not just an image that's pretty, it's a chemistry image that teaches us about the chemistry and physics of these regions, which is very cool. You can look up raw JWST images, but I won't do that right now. Next question.
Yeah, to follow that was just, so how do you know which elements are present if you're not using the spectrum to determine them?
Yeah, so in things that are in our backyard,
Hello.
that gas isn't moving forward towards us or away from us. chemistry, like if you have ever had in your classrooms or something like one of these like atomic uh like uh like because of the energy levels where the photons are moving, you can essentially and like see, wow, this exact wavelength of light comes from hydrogen. 65, 63 corresponds to an energy orbital between one of the electron levels to another. And that gives off a very characteristic red color that then you could put a filter right on that and say, oh, I know this has to be from hydrogen, right? Hydrogen is very omnipresent. So there's multiple of these specific lines in the near infrared from different energy levels, the Passion series as opposed to the Balmer series, as opposed to the Lyman series. But the Passion series is near infrared, which lets us do that. And so it turns out that elements have very specific chemical fingerprints or photon fingerprints that are at very specific wavelengths that you could focus on with filters. I know one of my favorite is oxygen, which has a very green color at 5,007 nanometers. No, 5,007 angstroms, 500 nanometers. And that is like a very green color. And so often you put a green filter and see all this beautiful oxygen tendril gas. Other questions?
Oh, thank you. So what has been some of the biggest surprises with the JWST data?
One of the things
is expected or
yeah, one of the things is that when we launched the telescope, we didn't think we'd find this many distant galaxies. That actually there are more bright distant galaxies than we predicted. And that's okay. It was not something where it breaks our models and breaks our understanding of the universe. We just knew that Hubble couldn't see a lot of these, and so there were big error bars here. There are a couple other things. A galaxy that I found, so I showed you this, or let me just show you this, where you can see this thing where it says clearing begins and the space around stars begins to clear up in the top left corner. This region of the universe was where the universe had these like little bubbles that were slowly being inflated, where the bubbles were in a bunch of like fog. And the first time we started to see some of this fog clearing, you can see a little bit farther out where the fog is essentially cleared by clearing completed down here, right? Like, maybe a billion years later. I found a galaxy that's in this fog that shows a signal that when I showed this spectrum to other scientists, they were like, there's no way that this is the case. And this indicates that the clearing had begun and you get these big bubbles earlier than anyone thought. This is an object called Jade's GSZ13-1, LA1, which is a Lyman alpha, it doesn't matter. But like, this was a very exciting thing. But on top of that, like I'm finding brown dwarfs, we're finding massive galaxies, we're finding these types of objects called little red dots. If you're interested in hearing me speak about little red dots, I'm doing a public Zoom lecture next Thursday, not this upcoming Thursday, but the next week Thursday at Space Telescope Science Institute. I can put that in the chat. STSCI, do I have my STSCI, Kevin Hainline, red dots? Yeah, here we go. I'll put this in the chat if you're interested in watching this, because it should be a public lecture. If you're like, I gotta have more Kevin, let's put this in the chat right here. But this is the thing that's next Thursday. I'm giving a whole talk about these. And that's a super fascinating thing. What are these weird red dots we're finding? Are they weird growing black holes? So I think that there's lots of stuff. And that's not including all the stuff that's being found in our nearby galaxies, in the Milky Way. I'm an extragalactic scientist, but I'm just like puzzled by all of this weird, cool stuff that's out there. Other question.
So one that was just posted here, lofty question. Do you think anything larger than the observable universe?
I don't know.
Yeah. Control all the universes?
The universe is everything. And it is by definition the entirety of its energy, because that's how you define the universe. So the question is there anything outside the universe? And unfortunately, because we're inside of it, it's pretty hard for us to tell if there's something outside it. It's hard to tell if there's something outside of a thing that is by definition all that you can see. There are some theoretical models of by theoretical physicists about multiverses or other, but I don't know. This is beyond my pay grade. It's a very good question and it'd be really fun, but for right now, the universe, as far as we know, is infinite in all directions, and it is an infinite, it contains the entirety of everything. And so what's outside of that? I don't know. All we see is going back in time, so we can just see things go back to the beginning of time. We can't see things out because it would take an infinite amount of time, or even longer for us to get these things from way out there. Anyway, I've been given the red light. It was wonderful to talk with you all today, and I hope you have a really great time. Thank you so much for all of your incredible questions and for listening to me. Thank you.
Now, before you go, as you are well aware of, Dr. Hainline, we always like to give you a thank you for spending so much time with us. And so we once again have planted trees in your honor, and you will get a certificate talking about the trees. This time we're just planting them in the greatest area of need. So, you know, the Arbor Day Foundation does a phenomenal job of restoring areas that have suffered wildfire damage. And so thank you so much, as always, for your time and your expertise and your passion and your statement about the importance of science for all citizens, and for inspiring our teachers to continue to educate our students to become science literate citizens, which we desperately need.
Thank you so much. I'm posting a link to all of the images that I said are found on the Webb Telescope page, and you can go and find them all and read all about them. Please use this as a resource for your classrooms and stuff. But anyway, it was so wonderful to talk with you all. Have a great rest of your night. And if you have other questions, look me up. Come watch my Space Telescope public lecture next week. You know, it's real easy to find me online, you know, and if you're in Arizona, I love coming and talking to school groups and talking to them through Skype with scientists. Anyway, bye everybody.